In this video, we are going to be discussing transformations. Or, essentially how to go from one frame of reference to the next. And so if we talk about the Galilean case, then, if I have a person who is moving with some velocity v, and another person over here declares themselves to be at rest, then this is the barred system. So x bar, and then this person would measure a distance x from there. So the transformations then would be that x bar is equal to x minus that distance traveled by the velocity. There's no change in y or z because I've declared this person's only running in the x direction. And time is the same in both frames. So this person here would measure a time, this person running would measure a time for themselves as t bar, and in both cases the time is absolute, that the time is the same for both frames. Now if we now move on to special relativity, what we have is what's called the Lorentz transformations, which say that x bar is really gamma x minus v times t. Y, in this case, doesn't change because I've defined the problem to be only moving in one direction. Z doesn't change, but the time follows the time dilation. So you notice now that in the Lorentz transformation, as opposed to the Galilean transformation, time now has a spatial component added into it. In the Galilean case, t was just equal to t, but now in special relativity, now what we have is the space is incorporated into how the time is going to change between frames of reference. Okay. So if you want to take the inverse, the easiest thing to do is to notice that the inverse is just changing the direction of the sign of the velocity, because in the inverse, this person's standing here, and the other person is now moving away with some negative v. So instead of having to work through the algebra, why don't we just switch the signs? And what we get is x is equal to gamma x bar plus vt. Y is still equal to y bar. Z is still equal to z bar. And t is now equal to gamma t bar plus v over c squared times x bar. Okay. Because, since no frame claims itself to be absolute, all we have to do is just, change our perspective on the different frames. Okay, so what I want to take a look at now is one of the examples in the book, and that is this example 12.6. Which says that we have a particle that moves a distance dx in a time dt. Therefore, the particle's velocity is dx dt. Now, in the barred frame, so I'll call it S bar, is moving with velocity v with respect to s. So again, let's say this is our familiar train. Inside this train car, s bar is moving with the velocity u, but the train itself is moving with the velocity v, and now, so this is frame s, this is frame s bar. And so we want to figure out how to add up these velocities. If you have someone moving with a velocity while the frame is moving with a separate velocity. So what we can do is we can take a look at the differentials and say dx bar is gamma dx minus v dt, and dt is gamma dt minus v over c squared dx. And we're not going to worry about y and z because they're not changing. Okay, so therefore u bar, so this should have been a u bar. U bar is dx bar dt bar, which is gamma dx minus v dt over gamma dt minus v over c squared dx. And so the gammas cancel. If I now factor out a dt, or essentially make this dx dt minus v over 1 minus v over c squared dx dt, then what I have now is u minus v over 1 minus u v over c squared. So in the end, the transformation of velocities is the difference in the velocity measured by the person outside, u, minus the velocity of the moving frame, divided by this factor which combines both of the velocities. So now what we've dealt with measuring time between frames, we've dealt with measuring distances between frames, and now we're looking at measuring velocities between frames. So basically kind of, emphasize the fact that u is measured by s bar in s bar, u is measured by s in the s bar frame. So u is essentially measuring the velocity of the person in the car by the person outside the car. Okay. So now we have transformations for time, distance, and velocity. Okay. So the next thing we can take a look at is what the book calls the structure of space-time. And we can kind of simplify things by saying x is equal to x1, y is equal to x2, z is equal to x3, and speed of light times t is equal to x0. So these superscripts are just labels. They're indices. They're not actually exponents. And beta is the relative velocity with respect to the speed of light. So what we're doing now is we're putting time on equal footing with space. So the speed of light times time now equals a length. And so now we have a four-dimensional, so a 4D lengths. So we have x, y, z, and ct are now the four-dimensional 4 dimensions that we live in. We can now rewrite these Lorentz transformations as time. So CT is equal to gamma CT minus beta x1. x1 is equal to gamma x1 minus beta x0. And then x bar 2 is equal to just x2. And x3, which is our z component, doesn't change. It's not transformed. Because, again, I'm just restricting it to the x direction. We're only moving in the x direction. Okay, writing it this way, I can now write it down in matrix form, where we now have all of the x bars as a vector. And then I have a transformation matrix. Times my vector in the other frame. Like so. Okay. So this is the Lorentz transformation. So I can write it down now algebraically as x bar mu is equal to the sum of nu goes from 0 to 3 of my transformation matrix, nu mu, x nu, where mu runs from 0, 1, 2, and 3. So I can pick out each of those dimensions. I can pick out CT if I set mu equal to 0. I can pick out x if I set mu equal to 1. And it's now equal to this. So this matrix is now my Lorentz transformation. These x's with the indices mu or nu are what are called 4 vectors, because it's a vector with 4 dimensions. And what we saw before in our math methods class is that we can write these as covariant vectors, where the index is in the subscript. And in this case, it would be x0, x1, x2, x3, and we can write them as contravariant vectors, where it's in the superscript. And the difference now is that I have a minus CT, and x, y, and z stay the same. So that's the only difference. The minus sign comes about in the Lorentz transformation because it's essentially this cofactor. It's like a Jacobian that's multiplied through. Okay, the interesting thing now is when I take the dot product, the dot product, you'll remember, is if we write it out with summations, it's, say, mu is equal to 0 to 3, a mu, b mu, in this case, would give me minus a0, b0 plus a1, b1 plus a2, b2 plus a3, b3. And these are all indices. None of these are exponents. But from now on, I think what we should do is we should use the Einstein summation notation, where we don't use the sum anymore. Instead, we just use the upper and lower indices, which will give us the same thing. Okay. And okay, so we'll stop here, and then we'll continue this discussion on Lorentz transformation in the next video.